All right, this is the lesson from Unit 13, Day 2, Trigonometry, Day 2. And like usual in class, I'd like to start up with a warm-up. So you can see the warm-up on your screen right now. If you're watching this at home or not in class, please take a minute to pause the video and see if you can answer both of these questions. And when you're ready to go on and check your answers, hit play, and you can see if you were correct or not. Okay, so I'm assuming that you paused it and you tried it for a while. Now let's see how you actually did. Okay, so number one, I want to sketch 17 pi over 6 as an angle in standard position. All right, so remember what that means. We've got 0, pi over 2, pi, 3 pi over 2, and 2 pi. And I would really like to have you continue labeling those quadrantals until I tell you otherwise. All right, so when I look at this first, I see that we're over 6. So what would I want to think of pi as? 6 pi over 6. And I got to get all the way to 17 pi over 6. So you got to keep going. So that's 6 pi over 6. Go over to 2 pi. What would that be is something over 6. 12 pi over 6. 12 divided by 6 equals 2. Still got to get to 17. So think about it. If I went 6, 12, another 6 would bring me to 18, right? So this would be 18 pi over 6. And then that's far enough because I needed to get to 17 pi over 6. So 17 is 1 less than 18, which means my angle would be right here. And I would have gone all the way around once and almost halfway around the second time. So that'd be my angle theta. So I'm starting on the x-axis, that's standard position, initial side, and terminal side. So we're in quadrant 2. All right, so down here, we didn't specifically talk about all this, but I wanted to see if you could figure it out. State the equivalent degree measurements. It's going to be really important to be able to think of degrees and radians kind of interchangeably. So pi, you should all know. Pi we know is right here, and pi is the same as 180 degrees. Okay, now let's skip to some others that you should know right away for a minute. Pi over 2. Pi over 2, that's up here. That's the same as 90. 3 pi over 2 is down here, 270. And 2 pi would be all the way around, so that's back to 360. Now, these ones I skipped in the middle are going to become pretty important for you. Pi over 3. Think about what that actually means. That means you're taking this distance between 0 to pi and splitting it up in 3 equal pieces. So what would that equal? Well, if I take 180 and split it up into 3 equal pieces, you should be getting that pi over 3 is the same as 60. Pi over 6, same idea. If I divide 180 into 6 equal pieces, what would you get? 30. And pi over 4, divide 180 into 4 equal pieces, and you get 45. All right, now these 3 angles, pi over 3, pi over 6, and 45, or equivalently 60, 30, and 45, are going to play a big role in what we do today and what we do for the next 2 or 3 weeks. So try to start figuring out a way to kind of associate those and memorize those quickly. I think of pi over 4 and 45 going together because of the 4s. The 4s kind of matching up there. Pi over 6 and pi over 3, that trick doesn't work so well. You have to kind of flip-flop it. So pi over 3 goes with 60, pi over 6 goes with 30. We'll revisit that in a couple minutes in the lesson here. So before we go on, there's your random fact of the day. Who knew? Okay, so now we need to go over to today's notes. And we're going with special right triangles and right triangle trig. I think you've heard of most of, if not all of what we're going to talk about today. I posted a blank copy on my website of this note sheet. So if you don't have a blank copy, please print one out. If not, just follow along the best you can, but I think it would help you more if you could print it out and actually fill it in as we go. So if you haven't printed it out yet, please pause this video and do that. But otherwise, if you're ready to go, here we go. Part 1 is on special right triangles. It says use the Pythagorean theorem to find the missing side for each of the triangles shown. All right, so you all know the Pythagorean theorem. What's the Pythagorean theorem? A squared plus b squared equals c squared. Okay, so remember with that Pythagorean theorem, the c squared always has to represent what? Right, the hypotenuse. Okay, so if I've got 1, 1, I could do 1 squared plus 1 squared equals c squared. So we get 1 plus 1 equals c squared. So 2 is c squared. Then to solve for c, we take the square root. And remember, I normally would say plus or minus the square root here. But for at least today, we're just talking about lengths of a triangle. So we can talk about it all in terms of its positive values. So this is radical 2. All right, try the next one. 2 and 2. We have 2 squared plus 2 squared equals c squared. So 4 plus 4 equals c squared. 8 equals c squared. Take your square root. And get c equals radical 8, but reduce it. Think of it as 4 times 2. So that 4 is going to come out as a 2, and left with radical 2 still. So that hypotenuse is 2 radical 2. All right, now look at what we got for the first one. Look at what we got for the second one. There's a pattern here. Make a guess of what you think the third one's going to be. All right, let's see if your guess is right. Here's 5 squared plus 5 squared equals c squared. So 25 plus 25 equals c squared. 50 equals c squared. Take the square root. And c is radical 50, but again, we can break that down. This is really 25 times 2. So that 25 is going to come out as 5, leaving me with radical 2. So there's 5 radical 2. All right, now what's the pattern here? If these two sides are the same, we have 1, 1, 1 radical 2. 2, 2, 2 radical 2. 5, 5, 5 radical 2. If you jump down here for a second where it says in general, it says if I've got this triangle, if I say this side is x and this side is x, what would the hypotenuse be? It'd be x radical 2. So whenever you've got two legs of the triangle equal, the hypotenuse has to be x radical 2. And this is only for right triangles. Okay, now let's go back to this for a second. From geometry, you should know there's some theorem where if the two sides are equal, what do you know about the angles opposite them? Well, if the two sides are equal, then the angles opposite them also have to be equal. Okay, well, if this is 90 degrees, what do the three angles in a triangle always add up to? 180. So if three angles add to 180, I've already used that as 90. That means I have 90 left to work with. So between these two angles, I have to get 90 degrees. Since they're equal, if I just divide 90 by 2, that means that each of those angles is 45. And that's going to be true whenever you've got a right triangle with two sides equal. You have a 45, 45, 90 triangle. Okay, so down here we can also fill in that this angle would have to be 45. This angle would have to be 45. But I also want you to get used to thinking about those in radians. From the warm-up, we said 45 is always the same as pi over 4. Remember, those 4s match up. So pi over 4 or 45. All right, now the other special triangle we're going to be working with have a pattern as well. So let's use the Pythagorean theorem again. Here I've got 1 squared plus radical 3 squared equals c squared. So this is 1 plus radical 3 squared is just 3 equals c squared. So 4 is c squared. Take the square root. And we just got the hypotenuse, or c, is 2. I try with the next one. I've got 2 squared plus 2 radical 3 squared equals c squared. Well, 2 squared is easy, that's 4. 2 radical 3 squared is a little trickier. You've got to square the 2 and square the radical 3. So you're thinking 2 radical 3 times 2 radical 3. Well, 2 times 2 is 4. Radical 3 times radical 3 is 3. 4 times 3, that whole thing comes out to be 12. Essentially, you are taking that squared and putting it to the 2, putting it to the radical 3. So 4 times 3, you get 12. So that equals c squared. So I've got that 16 is equal to c squared. Take the square root, and c is 4. Okay, now, again, there is a pattern going on here. When I have 1, technically this is 1 radical 3. 1 radical 3, that's 2. When this is 2 radical 3, that's 4. What do you think it's going to be if it's 5 radical 3? Well, hopefully you have a guess again, but let's see if you're right. So 5 squared plus 5 radical 3 squared equals c squared. 5 squared is easy, that's 25. What would 5 radical 3 squared be? 5 squared is 25 times 3, 75. Oops. So I get 100 equals c squared. You guess 10? Well, if you didn't, you were wrong, because that side is 10. So the other special triangle, if I have an x here and an x radical 3 down here, whatever that x value is, it's doubled with the hypotenuse. So that means if this is x and this is x radical 3, hypotenuse would be 2x. Hopefully those look familiar. I think you did those in geometry last year. Now the angles for this second one aren't as easy to come up with as the 45s were. But if you had a protractor and you actually measured these out exactly, you would find out that these are all similar triangles and they all have the same 3 angles. We've got the right angles already. The angle next to the radical 3 is always 30. So in this case, it's up at the top there. And the angle on the other side, if I've got 90 and 30, I've got 120, I've got 60 left to get to 180. So this is always 60. So in my triangle down here, I see the radical 3. The angle that's next to that, or adjacent to it, is 30. The one across is always going to be 60. I remember that by thinking that the 30 and the 3 and the radical 3 kind of match up too. Those go next to each other. Now, what are these two angles in terms of radians? Remember, I want you to be quick with those. 60 is pi over 3, which we saw in the warm-up. 30 is pi over 6. Remember, those ones kind of flip-flop. The 6 goes with the 3 goes with the 60. All right, so those are our special triangles. We're going to be working on those to answer the rest of these questions. Okay, so here we go. Determine the missing sides and angle for each triangle. So if you see 30, 60, and a 4, you kind of match it up to this triangle I drew up here. 4 is next to the 60, so this is where x would normally be. This is x radical 3, and this is 2x. So if x is 4, what's x radical 3? This is 4 radical 3. And if x is 2x, and if x is 4, 2x is 8. That's all you got to do. 45, 45, 90. We know the legs are both x, and this is x radical 2. So 10 is x, so that's easy. This side is 10. This side is 10 radical 2. All right, ready to go on to the next page? Of course you are. Here we go. Okay, now I threw radians in. Remember, it helps. Pi over 3 is the same as 60. And pi over 6 is the same as 30. So the 6, since that's next to the 60, that's what? That's x. So down here is x radical 3. So in our case, it's 6 radical 3. And the hypotenuse is always 2x. So if x is 6, this hypotenuse is 12. I see pi over 4 is in number 4. What's that mean? Those are both 45. Now this one's a little bit tricky. What's on the hypotenuse normally of a 45, 45, 90? X radical 2. And these sides are just x. So we know right now that 5 radical 2 is where x radical 2 is. Okay, so what's x? Well, hopefully you can see pretty quickly that it's 5. If you needed to actually see it out mathily, you could divide by radical 2 and get that 5 is x. So that means the missing sides are 5 and 5. Number 5 is back to a 30, 60, 90. 16 is where what normally is? 2x. So what does that mean about x? It means that x is 8. So x is always the side next to 60, so this is 8. And next to 30, we always have x radical 3, so that's going to be 8 radical 3. 6, we're back to 45, 45, 90. This 7. The 7 is where what normally would be? X radical 2. So this one might not be as easy as number 4 was. So I got to say 7 equals x radical 2. If I want to solve for x, what do? I divide by radical 2. Okay, so I get that 7 over radical 2 equals x. But I think we talked about simplest radical form before. I don't ever want to leave a radical in the denominator, and that's going to go for the rest of the year. If I see a radical in the denominator, I need to get it out. So what can I do to this fraction that would keep it an equivalent value, but get that radical to not be in the denominator anymore? The trick is multiply top and bottom by radical 2. Because this is just like multiplying by 1. I'm not really doing anything there, right? Radical 2 over radical 2 equals 1. And when I multiply something by 1, it doesn't change the value of it. So if I'm multiplying top and bottom by radical 2 here, what's radical 2 times radical 2? Why does that help me? So that's just equal to 2. On the top, I have radical 2 times 7, which we would just say is 7 radical 2. So that's called rationalizing the denominator. We've got 7 radical 2 over 2, and that's an equivalent answer to 7 over radical 2. Okay, now back to our problem. That's what x actually is. And we know in a 45, 45, 90, these two sides are x. So that means this is 7 radical 2 over 2, and this is 7 radical 2 over 2. All right, down to number 7. 30, 60, 90 again. The 15 is where what would normally be? 2x. So that means x is, you can just say 15 over 2 or 7.5. As long as you don't round it, 7.5 is fine. I'm just going to leave it as 15 over 2. So next to the 60, that's where our x always is, 15 over 2. And next to 30 is always x radical 3. So we have 15 radical over 2, radical 3. No radicals in the denominators, so we're fine. Number 8, pi over 4s. Remember, those really mean 45. 3 is where what would normally be? X radical 2. Okay, so we've got that situation again where I have to solve 3 equals x radical 2. So if I want to find what x is, I've got to divide out radical 2. So I get x is 3 over radical 2. But I don't want those radicals in the denominator, so what do? Multiply top and bottom by radical 2. That means an equivalent form of x is 3 radical 2 over 2. Since that's x and both of these sides are x, 3 radical 2 over 2, those are our answers. All right, a few more here. Angles are gone. But if this is 2 and 2, this must be an x radical 2 triangle. So if x is 2, x radical 2 is just 2 radical 2. Now, if the angles are missing, I want to see those too. Unless it's specified, you can choose 2 degrees or radians. So what type of angles do 2 radical 2 triangles have to have? That's always the 45, 45, 90 triangle. Remember, the angles have to be the same as the legs are. And the sides opposite an angle are always equal. How about over here? We've got x radical 3, so obviously x is 6. So what goes in the hypotenuse? Usually x, 2x, x radical 3. So that means the hypotenuse should be 12. Now fill in your angles. I see the radical 3, so I always go to that one first. What angles has to be there? The 30, the 3 goes with the radical 3. So this has to be 60. How about 1 and 2? Well, it can't be 1, 1, radical 2. So it must be 1, 2, radical 3. This would be x, 2x. So x radical 3 is just 1 radical 3, or just radical 3. What are the angles? Hopefully you're jumping to this one first. Next to radical 3 is the 30. And we have the 60 over here. All right, last one, and then you can try a couple. I see 1 and radical 2. Well, that could be x, x, x radical 2. What's x? All right, just 1. This is a 1. 1, 1 radical 2. Angles, whenever the legs are the same, angles are the same. This has to be our 45, 45. 11 and 12 are going to be big ones in the next couple days. We're going to be using these ones a lot. We'll talk about why tomorrow. Okay, so your turn. Take a couple minutes, see if you can find all the missing sides and angles of these two triangles. Pause the video for a second. Fill them on your phone. And when you're ready to check to see if your answers are correct, unpause, and we'll keep going. All right, so hopefully you've had a time to try those on your own. This is an x, x, so this has to be x radical 2, so it's going to be 3 radical 2. These are missing angles, 45, 45. Over here, this is x, x radical 3, so x is 2, so this side is 2x, which means this side is 4. And the 30 should always be next to the radical 3. The 60 is your other angle. All right, so that's the end of the first part. Hopefully that was a good refresher. Hopefully you've seen that before. Excuse me. Over on the last page is the second part of today's lesson, which is right triangle trigs. When you're ready to flip over, go ahead and do that. All right, here we go. Here's a couple of random triangles. It says label each side as opposite, adjacent, and hypotenuse in relation to the given angle. Well, hypotenuse is always across from the right angle, so that's got to be the hypotenuse. Adjacent means it's the side next to the given angle. And opposite means it's the side across from the given angle. Over here, I'm giving you this angle. I always label hypotenuse first because I know that that's got to be across from the right angle. Adjacent is the one next to it, and opposite is the one across. Okay, now hopefully you've heard of these three trig functions before. I know you did in 9th grade, or maybe last year. Sine of theta, cosine of theta, tangent of theta. Those all represent ratios of sides of triangles. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. And the way that people always remember those is by using SOHCAHTOA. So, sine is opposite over hypotenuse. Ka. Cosine is adjacent over hypotenuse. TOA. Tangent is opposite over adjacent. SOHCAHTOA. Okay, so using those trig definitions, it says find the values of the indicated trigonometric functions, express answers in simplest radical form. So remember that means the radicals have to be simplified and also no radicals in the denominator. So here's my triangle. Let's do the thetas first. This is always going to be the hypotenuse. If I'm talking about theta, then that's the adjacent side. This is the opposite side. So sine, which is opposite over hypotenuse, would be 4 over 5. Cosine, which would be adjacent over hypotenuse, would be 3 over 5. And tangent, which would be opposite over adjacent, TOA, would be 4 over 3. And all those are simplified, don't need to be reduced, so those are our final answers. Okay, now when I switch to alpha, that's what this little guy is over here, that's alpha. Hypotenuse doesn't change. Hypotenuse is still hypotenuse. But now, if I'm talking about alpha, then 4 is the adjacent side, 3 is the opposite side. So sine of alpha, opposite over hypotenuse, opposite is 3, over hypotenuse is 5. Cosine of alpha, adjacent over hypotenuse, adjacent is 4, hypotenuse is 5, 4 over 5. And tangent, opposite over adjacent, opposite's 3, adjacent is 4, 3 over 4. Now if you look down at the next one, I've got 2 and 8. I didn't show you the other side. How do I find the missing side? Pythagorean theorem. Right, okay, so Pythag it up. Pythag. We've got a squared plus b squared equals c squared. What side has to be c squared? That's right, the 8. So it's 2 squared plus b squared equals 8 squared. So 4 plus b squared equals 64, which means b squared equals 60. Take the square root of that. Remember, simplest radical form, we got to break that up if we can. So 60, well, I know 4 goes into that. That's a perfect square. 4 times 15. So I can pull this 4 out. 2 radical 15. So this side is 2 radical 15. All right, now I want sine, cosine, and tangent of x. So if this is x, obviously this is hypotenuse. 2 radical 15 would be adjacent, and 2 would be opposite. So sine of x. So opposite over hypotenuse. Opposite is 2, over hypotenuse is 8. We can reduce that to 1 over 4. Cosine of x, ca, adjacent over hypotenuse. Adjacent is 2 radical 15. Hypotenuse is 8. We're allowed to reduce the 2 and the 8 to get radical 15 over 4. Radicals on top, so we're good. That's simplest radical form. Tangent of x, TOA, opposite over adjacent. Opposite is 2. Adjacent is 2 radical 15. Now there's 2 things going on here. We can reduce the 2's. I would do that first. So now it's 1 over radical 15. And you also don't want that radical 15 in the denominator, so remember what we do. Multiply top and bottom by radical 15. It's the simplest radical form again. So we have radical 15 over 15. Again, just to put it into perspective, I think you understand, but 1 over radical 15 is that number. Radical 15 over 15 same number. They're equivalent. It's the same thing. It's just a long time ago, mathematicians started using simplest radical form just as a convention because it was easier before the time of calculators to divide radicals than to divide by radicals. Now it doesn't really matter so much, but it's just something that's kind of become accepted among the mathematics community, so we just play the game and keep doing it. So keep doing it. All right, last one down here. One for you to try. Pause it again, see if you can do it on your own, and then restart it, and I'll check your answers for you. All right, did you try it? Hopefully you did. We need the missing side, so we got to use Pythag again. A squared plus b squared equals c squared. Hopefully you put in 4 for c squared. Otherwise, we have radical 7 squared plus b squared. What's radical 7 squared? Just 7. So 7 plus b squared equals 16. Subtract 7, b squared equals 9. Comes out nice. B is just going to be 3. Okay, so now I'm talking about beta. That's what this is. Obviously, this is hypotenuse. Next to beta is the adjacent, radical 7. Opposites to 3. So sine of beta, so opposite over hypotenuse. Opposites 3. Hypotenuse is 4. Nothing to reduce there. Cosine, adjacent over hypotenuse. Adjacent's radical 7. Hypotenuse is 4. Nothing to reduce there, and the radical's in the numerator, so that's okay. And TOA, opposite over adjacent. Opposites 3. Adjacent's radical 7. Don't want that radical in the denominator, so multiply top and bottom by radical 7. We get 3 radical 7 over 7. All right, so you did it. That's the end of it. Worksheet is on the website if you don't have a copy of it. So please print that out and give it a shot. And you have the answer key, so use the answer key for the unit. Check all your answers, make sure you're doing it correctly. And I will see you in class tomorrow. Good luck.